Again. Uh, Ian has teaching, so he had to leave. We are now moving to our final talk before the lunch break. This will be a lecture on Introduction to General Relativistic Magnetohydrodynamics, and it will be delivered by Philipp Mösta. Philip is a professor at the University of Amsterdam, and he is currently focusing on MHD simulations using GPUs. So I'll let you know when you have 5 minutes left before the questions, and you can start whenever you are ready.
Perfect. Thank you so much for the introduction and also welcome to everyone in the audience. I'm very happy to introduce you to GRMHD. As we're going to do this in about 40 minutes, I'm going to keep it pretty streamlined, but I've also included at the end some further material where you can go online and have a look or revisit some of the concepts, so that you can deepen your study of that if you would like to. Um, to get started, where is GRMHD important in astrophysics? And this is really an incomplete list of a very biased set of topics that I personally have a lot of interest in. But so generally, magnetic fields and hydrodynamics in astrophysics play a role in almost everything and anything. So they're very important in accretion disks around black holes. They are, for example, the primary source of viscosity in those disks and mediate accretion, and how those accretion flows can then be visible. That, for example, is super important in accretion onto neutron stars as well, X-ray binaries and things like that. They also play an important role in supernova, and specifically in supernova that have what we call a magnetically powered jet, which is not your default supernova explosion, but where you have a very collimated outflow. Um, they're also, of course, important in binary neutron stars. I think we've already heard a little bit about initial data for some of these compact object systems. But here again, they are crucial for determining especially the electromagnetic emission from these systems. So what kind of outflows are we getting? How magnetized are these outflows? How does that, for example, connect to the short gamma ray bursts? Or in the supernova case, the long gamma ray bursts. And they are also important for shaping the outflows of heavy elements that then ultimately make the kilonova. So they are important across the board, and maybe most importantly, they also play a crucial role whenever there's turbulence involved in a system. So when we have small scale chaotic motion where just the presence of even a weak magnetic field can significantly and drastically change the dynamics and the behavior of that system. So it is very important to understand the effect of MHD, even if the system is not extremely magnetized, as turbulence plays a crucial role in many of these settings that I've just introduced. So that as much for the astrophysical setting, but let's get into some of the more fun equation part. And so I think you already had an introduction to numerical relativity yesterday morning. So the first part here, the Einstein's equations, you should already be familiar with and how to hopefully numerically solve them now. What we're adding now is basically the equations of hydrodynamics, and this is what you're seeing in the second box here. So this is really basically how we can model stars or any kind of astrophysical system essentially as a fluid. And what we basically have here is conservation laws. So we have mass and momentum conservation, and then we have energy conservation as well. And these are basically the underlying conservation laws, and we're going to go into how these then kind of go into the detailed equations in a little bit. What we also need, of course, is an equation of state, and that connects nicely to the talk that we had just before. And that is important for closing the system and figuring out how the fluid behaves. What now makes this MHD is really this last box on this slide, which are essentially adding Maxwell's equations in GR to that. And this is what you're seeing at the bottom. And this really adds while you think it adds just a few equations, it really makes, for example, the numerical methods that we need to solve these systems, and I think you're going to hear about this tomorrow also from Ian, um, the numerical methods that we need to solve these systems much more complicated as soon as we include Maxwell's equations compared to just the hydrodynamic equations. So there's a lot of subtleties involved by doing GRMHD that may not be present in the hydrodynamic part alone. Okay, so let's go to the GRMHD equations. Um, so what are we talking about here when we look at some of these conservation laws? And you can basically go and look at a paper that introduces the Valencia formulation. This was in 2006 by Anton et al. That have essentially figured out how to write these GMHD equations in a conservative form. And what do I mean by a conservative form? It really means what we've written here in that first box, where we've basically taken these conservation laws written in abstract index notation that I've had already shown you on the previous slide, and convert them basically in what we've written here on the right side of this slide, where we basically have what we call a state vector, which is this boldface U. So that is really the set of variables that we use to describe our system. So this, in this case, could be something like the conserved density, the momentum, and so on and so on. And now we write down basically the time evolution of these equations, right? That's why we have the d by dt there, as a combination of these capital and boldface FIs, which are what we call the fluxes, and we'll go into what fluxes really means. But you can see here that this is basically a spatial flow of material or flow of information in the system, since you have the d by dx. And then on the right-hand side, you have the boldface S, which introduces the source term. So these are any sources or sinks of, for example, energy or anything else in your system. And the idea is now that we find methods of solving these systems, and we're going to go through these methods in a little bit of detail now in the next few slides. This involves what is called high-resolution shock capturing methods and Riemann solvers, and we find a way of solving these. This is for the fluid part. What we now have to add now is the Maxwell's equations, which give us, via the induction equation, an evolution equation for the magnetic field. And this is what you see in the bottom part of the slide. So we have the time evolution of the magnetic field equal some fluxes and source terms on the right-hand side. In the way that's written here, the sources are actually zero, as you see by this equals zero. So this is the overall abstract system that we're dealing with, and we're going to go through this now in a bit more detail and figure out how we can go about solving these systems. Okay, so what are our actual equations, right? Like I've introduced this state vector U, and you see here the definition of U. So this is what are called the conserved variables. So this is D, which is a conserved density. So you also see the definition of these variables below. So D is really just rho times the Lorentz factor. Sj is basically the conserved momentum, and you see how basically that combines, and you already see how now in the case of MHD, the magnetic field here already factors into that. So these terms on the second line here, B squared and B naught and Bj, this is already magnetic field contributions. What you also see is that this is a lowercase b, while we've defined the uppercase b as part of the state vector above. So the lowercase b is really the magnetic field that the fluid sees. So the magnetic field in the co-moving reference frame of the fluid. And because we're in GR, we have to be careful because all of these reference frames essentially are equal, but we do need to choose the one that matters here. So the fluid sees basically the lowercase b, which is the co-moving for magnetic field vector. This term b squared that you see in that first bracket where it's rho times h, which is basically density times the enthalpy plus b squared, that is also a special quantity in the sense that it has a physically intuitive meaning, and that is essentially what we call the magnetic pressure. So B squared is basically, or B squared over 2 essentially is the magnetic pressure. And that is something, for example, that we can use to compare to the fluid pressure to figure out how magnetized the system is. So one quantity that you may come across in your future career is what is called plasma beta, which is basically essentially the ratio of fluid pressure over B squared over 2. And that is a quantity that if larger than 1 is dominated by fluid pressure, if smaller than 1 is dominated by magnetic pressure. And that's a way how we can classify what is dynamically important in a fluid or in a plasma. Um, you see that also, for example, in the energy equation, this tau quantity, which is basically the conserved energy in this way, where you have in the second term, you specifically have P plus B squared over 2, which is exactly this kind of total pressure in a way, the fluid plus magnetic field pressure. So this is our state vector of conserved variables for GRMHD, and this is essentially what was introduced in the Valencia formulation. Why do we not use the primitive variables in the first place? That is because if we were to use those, we could actually not write down the equations in what is called flux conservative formulation. We'll go through that in the next few slides in a little bit, but basically we'll need to transform to these more complicated or less primitive and intuitive variables to be able to write down our equations in an advantageous form for numerically solving them. Okay, so this was what is on the left-hand side here for that's basically this U is the time evolution that we want to find for these quantities. And now what we have still to find is the fluxes and the source terms. And you see those now for the state vector and order in the same way as before. So we have this for D, we have this for Sj, for tau, and then for the magnetic field. And you see basically that the fluxes are basically a relatively complicated expression. And then the source terms, that depends a little bit on what we're actually looking for. So for the evolution equation for D, those are 0, and also for the magnetic field, they're 0. But then for the other quantities, we actually see our space-time variables and the stress energy tensor appearing. And this is basically how we get the coupling specifically from the geometric quantities into these equations as well. So this is the system we're dealing with, and I don't necessarily want you to focus on all the details of these individual terms, since this is something I think that is a bit too much for 40 minutes, but just so that you've seen what those look like and where you can go to look further into those. Okay, so why do we care about having this flux conservative form in the first place? And this basically comes down to like what we can achieve once we discretize the system. And so just for introducing this, let's go one step backwards and just look at a simple conservation law in 1D. Here you see a variable u, and we see basically we have the time derivative plus some spatial derivative of function f of u, and this is conserved, so it's equals 0. And so basically, there's now a theorem that if we can find a consistent numerical method in flux conservative form, then this converges to a function ux of t for the x that goes to 0, then ux of t is a solution of the conservation law. And this may seem trivial, but if we go into discretizations and things like that, it actually is not as trivial for all the choices we can make. So it's important that we have this quantity, since otherwise we have a much harder time to figure out if the discretized version of what we're trying to find actually converges to the real solution of the equation that we want to solve. So it is actually quite crucial to write down these equations in this form. Okay, so how does that go about when we want to solve this on a numerical grid? We again have this simple example of a du by dt, and now we want to solve this on our numerical grid. So we discretize it in the two variables that we have here as derivatives, time and space. And you see here we basically choose a number of points j to discretize our space, we get an effective resolution of delta x of the grid spacing. And we do the same for t, where we choose a number of points n and then have an effective delta t. What that looks like is basically something like that, where we have now drawn a diagram of x and t, and we have our points that are labeled xj, or specifically it's actually cells, because we're basically now looking at a 2D diagram, and this is basically the area that is denoted by xj. And then we have the interfaces between these cells at the indices j plus 1/2, j minus 1/2, and the same holds in time. So this is just a simple diagram of discretizing the system. We can now look like, when we want to find the solutions, how do we do this at the equation level? So here, basically, we go about and integrate in time and in space to get the solution. We've basically just applied the integrals in t and x to the equation that we had chosen. So you still see the du by dt, and you see the dfu by dx and the relevant integrals to it. And now we can basically write our conservation law in this integral form. Um, the the temporal derivative, of course, like we can always, so for each of these double integrals, we can always kind of write one of them in the relevant form of like the actual functions, which we've done when we follow this blue arrow and go into the second line. We can now also divide this by delta x, and this is one of the things where it's very clear afterwards why we're doing this. Initially, you may not immediately see why we're doing this, but basically we basically just divide the entire thing by delta x, and now we define some functions that are basically the solution at a given time, for example, here. So we define uj of n, and this is basically just for convenient notation as the integral in x over this function ux of t of n. If we plug this in, we can basically write now our solution uj at n plus 1, so at the next time, as the solution un minus what you see there on the right-hand side. And if we look at this now, this already looks quite similar to this flux conservative form that we have found before. And we can now substitute further. So we can define in a similar way this integral that we see on the right-hand side as our f of j at plus 1/2 and f at j minus 1/2. And if we substitute that in, we basically end up with the equations here, which is this uj n plus 1 is basically the solution at n minus what you see there, these fj plus 1/2 minus fj minus 1/2, and then all multiplied by delta t over delta x. And you see the definitions that we've used for that below to substitute this in. And basically, this is now exactly what we had seen before and what we call a flux conservative form for our numerical method. So now basically we can go make use of what we had said before, that in this case, we know that the solution converges to the continuum solution if we find a consistent numerical method, and then go about solving this numerically. So it was important to cast the equations in this way, and we can do this Valencia formulation for GRMHD has achieved exactly that, and now we can go and apply numerical methods to solve this on the computer. Okay. So one thing that matters now is like, how do we right? Like if we look at this first equation in this, we know the solution ujn at our current time. So what we need to find the time derivative and the step forward in time is basically this term fj plus 1/2 minus fj minus 1/2. What is important here again is that this is also at time index n, so at the current time. So now we need to basically compute, and these are basically, these f's are the fluxes. We need to compute those fluxes that we see there on the right-hand side. So how do we do this, right? Like we could do this relatively simple, and like maybe just to go quickly back. So what does fj plus 1/2 and fj minus 1/2 mean? These are basically the fluxes at the location at the cell interfaces. So this is basically these locations xj plus 1/2, xj minus 1/2 here, just as a reminder. To do this, we basically need to choose a discretization. And for example, we can choose one where we just do a centered derivative, a centered discretization of those spatial locations. So we can basically choose what I've written down here, where we basically do a forward in time discretization, meaning we discretize forward, and the centered in space one, where we basically evaluate this fj plus 1/2 in a centered way. So we take points on the left and right of that into account. So this is a very straightforward discretization. Turns out that this particular one is actually numerically unstable, and we could run a numerical analysis to figure out why. I think this is way beyond what we can do in the lecture here today. But there's more material online that you can have a look at. You don't need to do this discretization in full GRMHD to see it's unstable. You can actually do this for much simpler problems, and this is basically just a part of the discretization. But we could also choose a different one. And for example, we can use what is called upwinding, where we basically choose a one-directional stencil. So we basically take not the points at j minus 1 and j plus 1 into account to find the solution at an in-between point, but we take them to the right and to the left, and turns out that this is doing numerically much better, and one that we could use to actually discretize our system. So that is kind of the first thing we need to do, choose a discretization and what we want to do with it. To go further with that now, like we can also think about like what do those points or these labels that we've given our solution actually mean. And this is kind of where we come to what is the essence of finite volume methods. I think hopefully you'll hear more about this tomorrow as well in Ian's talk maybe, where we basically have to think about like, okay, so what does our function or solution at a point I or j actually mean? Right, like I've already talked before that this is basically not necessarily a point, but an area or a cell. And what that really means is basically that we take this quantity to be an average across that area and or across that cell, and then have a constant value there. So like in our cell delta x here, we have basically this function f of I, which is really, you can see this as an average across that cell. So this is essentially what we're doing with our discretization when we're looking at something where we interpret it in this way. There's other ways of looking at this, but for what we are trying to do, basically this is the basic choice that we're making. So what that allows us now is, right, like what is the underlying thing here actually? Now you see basically the discrete representation of this function f by giving it basically cell average values at each of these points. So basically if you were to draw a line around through this, then we could look at the actual continuous function f that we're trying to approximate with that. To solve this now and to solve what basically these fluxes are, right? Like if we look at, for example, this interface I plus 1/2 here, we basically have now a discontinuity at this interface between the two function values that are the cell averages from the left and the right. And we need to basically consolidate these two values. And this is what is essentially called solving the Riemann problem. So the Riemann problem really is basically solving the equations of fluid dynamics at a discontinuity. What you see here, basically where you have a value from the left and the value from the right along the x direction of where we've discretized this. This is true between any of these cells that we've just looked at in the previous finite volume representation of this problem. And we end up basically with a solution that we have to consolidate at this interface. And this is what solving the Riemann problem really does. So Riemann problem really is essentially finding these values, the flux at j plus 1/2. And we can do this in MHD exactly, but that is very complicated. And the main reason is that there's a lot of kind of physics that actually enter into how you solve the Riemann problem. There's basically different physical waves. So, for example, the magnetosonic speed, the Alfvén speed that you have to take into account when you're solving these solutions. I'm not going to go into the detail for how we solve the Riemann problem, since it's maybe not the best use of the time on MHD. But if you're interested in seeing more, there's basically two resources really that I want to point you to. One is Bruno Giacomasso's exact open source Riemann solver that you can see at this link. The slides will be posted later as well, so you don't have to note these down now. Where you can look at how a Riemann solver is solved exactly in MHD. That would be way too expensive to do in an actual evolution code for every iteration, for every point. So what we end up doing is actually using approximations of these Riemann solvers, and there's various levels. Some of them are like HLE, HLD, that take only part of that solution into account and then solve the Riemann problem in an approximate way. You can also see more details on the Riemann problem and how it's solved also in simpler settings in basically a computational astrophysics course that I'm teaching usually at the master's level, and where I have fully GitHub-based teaching material where you can kind of go through and do some of the Riemann problem exercises and the concepts behind it yourself. But basically, the Riemann problem is how we find the flux at fj plus one half or at j minus one half, the interface. And that allows us to then find the update of the solution, since finding the flux is essentially finding the time evolution of our quantity. Okay. How do we put this in action? And so what we put in action is basically using this in our solver and then basically run initially simple tests to figure out that our Riemann solver and our MHD evolution scheme is doing the right thing. What you see here is from our GPU code GRMX, a set of shock tube tests. So these are basically standardized test conditions where you start with a certain profile of a solution that has a step in it. So it's basically what is called has a shock in it, and then propagates with time to. The key thing about these shock tube tests is that they're relatively simplified and just done in 1D, and that we have an exact solution that we can find. And what you see here is basically the different quantities of the state vector. So you see density, pressure, velocity in X, velocity in Y, the Lorentz factor, and then just one of the components of the magnetic field, in this case By, and you see the solution found numerically, the red dashed line, and then the blue line, the exact solution, which we want to compare against. So when we initially write a code that solves the GRMHD equations, we then run through all these standardized tests where we know what the solution should be to figure out if our code is doing the right thing. And this comes back also to this theorem that we started from in the beginning for the flux conservative form, that you really need to be able to write down the equations in the right way to do these tests in a meaningful way that you can actually have trust in your code's ability to solve and converge to the right solution. Okay, so these were very simple numerical methods for solving this. We had started with just basically a piecewise constant representation of our solution in this Goodenough discretization. We've said that this was basically a detailed, sorry, a simplified discretization method. We can do this at higher order, and this is what typically called high resolution shock capturing methods, where we, instead of assuming a step function to represent our discrete solution of the continuum function, we can also do this with piecewise linear functions, and we can go to much higher order and kind of basically reconstruct our solution in much higher numerical order to more accurately approximate the continuum solution. Of course, the other thing we could also do is, right, we had chosen a particular number of points to discretize our space in X. We can, of course, also keep the actual representation of the function the same, but increase our numerical resolution. If we go to double the number of points, of course, even if it's still piecewise constant, we have a much better representation of our continuum function. So there's lots of dials and knobs one can play with. Um, Coming back now to adding in the magnetic field, and we had seen already in these when we wrote down the flux conservative way that the Maxwell's equations were kind of a special part in that, as in they didn't have sources on the right-hand side. And in that way, it makes it kind of simpler, and you don't actually necessarily need to solve the Maxwell's equations for a Riemann solver if you were just solving the Maxwell's equation, for example, in GR without a fluid there. But the complication in the Maxwell's equations really comes in from this additional constraint equation that we're getting. And I think this is probably also something you had heard about, hopefully yesterday, that when you do the 3+1 split of spacetime, you basically get the evolution equations and the constraint equations for Einstein's equations. Something similar happens for the Maxwell's equations. We write down the evolution equations that follow from the fully covariant Maxwell's equations, but we also get a constraint equation, and this is what we call the divergence-free condition, and this is this equation under the green line in those slides. And this basically just means that the divergence of the magnetic field has to be zero. And then on top of that, we have the evolution equation that we had already seen in this flux conservative form in the overall GRMHD system. So now you think like, okay, this divergence-free condition, that doesn't seem to be a big deal. It doesn't look very complicated, but this is actually where most of the complications for solving GRMHD in actual numerics come from. And if you don't do anything, so right, the first approach would just basically be, let's just evolve the magnetic field and hope that our constraint is satisfied and that we don't deviate too much. This turns out is not a good idea, since this will very quickly blow up, as we typically, instead of random error canceling each other out, we typically see these accumulating, and we very quickly deviate drastically from this divergence-free condition. So we need to find ways of making sure that we can actually keep that divergence-free condition satisfied. And there's basically three main methods. There's lots of variations of each of these methods, and there's pros and cons for all of that. But maybe we can start with the second one, because that is also something that is very akin to what is done in the Einstein's, or can be done in the Einstein's equations, to make sure that the constraints are satisfied. And this is what is called hyperbolic divergence cleaning, which is essentially what is constraint damping for the Einstein's equations. And what we do here is basically we introduce an additional field that is in the Maxwell's equation. So if you look at the first line here, basically this is the Maxwell's equations would be just the first term on the left-hand side. And now what we introduce is this additional field psi, which is a scalar that actually basically gets the value of whatever divergence we are creating. And if we now do the same that we've done before, we write down the evolution equations for B, and now a new evolution equation for psi, we can find a way of writing this down so that psi always acts in a way that it damps away and transports away from our numerical grid any divergence that we are creating by accumulating numerical error. So this is something that works well in the Einstein's equations for constraint damping. It also works quite well here. You have basically two things that you can decide. One is like, how fast is this damping happening? So how fast do you basically damp down oscillations, and what is the characteristic speed that you propagate those disturbances away on your grid? And then one can actually find quite nice methods of getting that to stably basically help you keep this diff b equals 0 constraint satisfied. What of course it won't do is make sure that diff b is always exactly 0, because basically whatever divergence you create, you essentially damp and then slowly transport away from the grid. So you're relying on this damping and the transport being more efficient than any divergence you're creating. The nice thing about this method is that basically it naturally works well with mesh refinement grids. So basically, you don't have to do too many special things to make this work for mesh refinement codes. This does not hold for some of the other methods. So basically going now to that first method, which is called constraint transport. And if you look at the references here and the times and dates for this, this is actually something that was used a long time already and has a lot of history in the field of GRMHD. Here, we're basically making sure that we're never really creating any divergence in our scheme in the first place. And the way we're doing this is by writing down very carefully what this time evolution of the magnetic field in the discrete space should be. So what you see here in the bottom is basically how we can think about the discrete time evolution equation for here it's just Bx, one of the quantities of the magnetic field, but we can write this down in an equal way for the other ones. And you see how basically the time evolution of this magnetic field, which naturally actually lives not at the cell center where we had when we did this Goodenough discretization, we had basically said like, okay, at a point j equals or I equals something, we have this cell average representation of this quantity, let's say the density. The magnetic field actually, if you look at it, because it's coming from the Maxwell's equations, naturally lives at the cell face. And then the evolution equation for that is essentially the fluxes are the electric field along the edges. So this is what you see in this little diagram there at the top, where basically the location of these different quantities are defined where exactly they live on the cell. So there is a way of writing down this time evolution equation for the discrete magnetic field in a way that you're guaranteed to not introduce extra divergence in your system. But you also see that this already looks relatively complicated in this bottom line. And it's also here actually very important that you write down exactly the right discrete operator. So not the continuum operator, but the discrete operator that you want to conserve. But you can do that. That gets relatively complicated, but it's something that also a lot of codes do. And basically in this method, the situation is different because you essentially have not the properties that we've just talked about for the divergence cleaning, but the case where you essentially don't create any additional divergence at any point in your time evolution. So you're basically stuck with whatever you have initially. So of course you have to make sure that initially you find divergence-free initial data, but then you're there. The other complication that comes in with this one is that this is not something that naturally out of the box works well with mesh refinement boundaries. So here really you have to be careful because this magnetic field essentially is defined in a discrete way. So if you now divide this cell phase into four smaller cells, but basically going to double the resolution, then this is not anymore true that the same operator is defined. And whenever you're starting to interpolate any of this, especially when you're doing time discretization, then this is not naturally doing well with mesh refinement boundaries. So one needs to write down very special operators, and that actually becomes very tedious very quickly.
Philip,
The
you
final,
have 5 minutes left.
yeah, it's perfect. I have like one or two slides more. So the final thing in this overview was like what is called vector potential evolution. So here we basically make use of the fact that we can basically write down the magnetic field as the curl of an additional vector field called the vector potential. So we're basically making use as something like akin to like how we can use the gravitational potential to basically have an overarching field that we use. And if we, of course, write down the magnetic field as the curl of this vector potential A, then if we take the divergence of the curl of something, and if this is a potential field, then we're automatically guaranteed that we're divergence free. And so now what we do in this method is instead of evolving the magnetic field directly, we actually evolve a different variable, namely this vector potential as part of our state vector. You see the evolution equation there at the bottom left side of the slide where we have dt of AI, and then we have a combination again of this bk and an additional gauge field phi. And this will guarantee that we will always have divergence-free magnetic field because the magnetic field is basically derived via the diff of the, sorry, via the curl of the vector potential. So now you might think like, okay, perfect. This is the method to go with since this is automatically always giving this by construction, even at the analytic level. But here it also gets complicated, mainly because of mesh refinement issues and because of this gauge field phi. So meaning here we have gauge freedom, which again, in principle is great, but as you've probably seen yesterday in the numerical relativity lecture, can also be a real headache to find a gauge that actually works well numerically and on the computer. The same holds true here. So there's been significant work in finding gauges, for example, that work well for in-spiral of binaries. One of the typical ones that's being used is the Lorentz gauge, but you can also use other gauges. And then on top of that, there are similar issues with the vector potential at mesh refinement boundaries where often additional dissipation has to be added or one has to do something careful when one actually restricts or interpolates these quantities. So this is a little bit akin to the constraint transport. And actually, in an interesting way, if you're doing this at a single refinement level, so a single grid, one can show that the vector potential method and the constraint transport method are basically identical up to machine precision in preserving diff B. But once you introduce AMR, it all becomes a lot more complicated. So in kind of review of this diff B equals zero constraints, different codes do different things. All these different methods have advantages and disadvantages that relates to how easy it is to numerically implement them, but that also relates to what things they actually preserve. For example, constraint transport, you can write down in a way with suitable operators to conserve magnetic flux at mesh refinement boundaries. Vector potential does not automatically give you that, and then it depends a lot on what kind of quantity, what kind of system you're looking at. If you have a lot of mass flow across mesh refinement boundary, maybe the vector potential is not ad hoc the best choice that you want to make. But if you're dealing with binary inspirers, for example, vector potential seems to be doing quite well, as it's a bit harder to get this to work in constraint transport. The divergence cleaning seems to be overall a bit more robust and applicable to a lot of different systems, but there you have to really fine-tune those coefficients that you're using to dampen and transport away things. So there isn't really one that is superior. Lots of different codes to different things, and I think you just have to carefully look at what you're actually trying to achieve when choosing these methods. With that, let me summarize and just point you to the two resources that I had also linked before. So one of them are my course notes on computational astrophysics, and the other one is Bruno Giacomazz's exact open source Riemann solver that you can play around with for MHD. And with that, let me thank you for your attention, and I'm happy to take any questions.
Thank you very much, Philip. It was a very nice talk. So I